Hello, guys. Good evening, all of you, and welcome back to Cheenta's Statistics Analytics Department. And today we are live with the problem of a seemingly multiple limits problem, but we'll see how we can attack this problem in a very interesting manner without knowing really high-tech stuff. So let's get started, guys. And if you have not solved this problem, please stop the video and solve it yourself and then come back, guys. So all the best, and let's get started. So it's asked that if x is a fixed real number, then what is the limit m tends to infinity? And first we would do we calculate the limit n tends to infinity cos 2n. It's an iterated limit, okay? So first we calculate the limit m. Just give me a minute. Yes, we calculate limit n tends to infinity cos 2n by x, and then after that it will be a function of m, and we then tend the limit of m to infinity. That's the whole idea. So let's see how we can solve this problem. Okay, so we will try to first decipher the limit of this. Okay, our aim will be deciphering the limit of this and then to find and to express it as a function of m, and then we will see that what the value of limit m tends to infinity f of m turns out to be. Okay, so there are a lot of options over here, but you can check this. So whenever options are given in your exam, if options are not given, the way to check like how to use options at an advantage is that you get a hint from the option. Okay, this is the direction I should think, and you can see that the direction you should think is about assuming whether x is irrational or not. This options are sort of throwing at you, say, see guy. So this is the hint you need to use for the like solution. So let's get started. So with the hint, so we need to assume two cases: x is a rational and x is irrational. Okay, x is irrational. X is irrational. And here x is rational. And let's say x is equal to p by q format if x is rational. Okay, so let's understand something. We need to find out limit n tends to infinity cos 2n whole to the power m factorial pi x, m factorial pi x. So pi p by q. Understand something very carefully, that we will use one result over here. The result is that cos x or cos a is equal to plus minus 1 if and only if a is an multiple of pi, right? A is equal to n pi format. Okay, so cos a is equal to plus minus 1 if and only if a is equal to n pi. That is, a is a multiple of pi if and only if. So therefore you can understand that cos to the power n m factorial p by q, or let's do it in general. Let's do it as in x, sort of. Let's not assume anything over here. So cos to the power 2n m factorial into x into pi is equal to 1, or rather if you just remove 2, okay, is equal to plus minus 1 if and only if what? Whole to the power n is there, so it's 1 plus minus 1 whole to the power n will be also plus minus 1 if and only if m factorial into x is an integer n. That is the only case it will happen, right? And therefore cos to the power 2n m factorial x into pi, whatever, if it's plus minus 1 whole squaring, it will be making it 1. Will be 1 if and only if m factorial x is equal to n, right? Same. So this is a basic idea, that cos to the power 2n into m factorial x of m factorial x pi is equal to 1 if and only if m factorial x is equal to an integer. Okay, and therefore what do we get from here? What idea do we get from here? Let's see. So therefore we get that cos to the power 2n. So what happens if cos to the power 2n is not equal to 1? So it must be less than equal to 1, right? So therefore cos to the power m factorial into x pi is less than 1 if m factorial pi cannot be expressed as, is not an integer, right? Is not an integer. And cos 2 pi m factorial into x pi is equal to 1 if and only if m factorial x is an integer, right? So therefore you can understand, let's call it n. So therefore you can understand that now इसके ऊपर if I do limit n tends to infinity cos 2n m factorial x pi, this will go to 0 if and only if in the first case, right, m factorial x is not an integer, and limit n tends to infinity cos 2n m factorial x pi. So you can sort of do cos square only, okay, just not n. You can just do cos square and then you take whole to the power n. It's like cos square whole to the power n. This is less than 1, so this will be to the power n will be going to 0. So it's square and whole to the power n. This will be going to 1 if and only if. So it's like this is less than 0, 1, and you are doing to the power n and you're tending it to infinity. So it turns out that this goes to 0. And if you're it's equal to 1 in this case if and only if m factorial x is an integer. So you can easily understand that depending upon the value of x, the two limits are different. Okay, so let me write it down again. So if m factorial x is equal to an integer, then cos square m factorial x pi whole to the power n, that is cos to the power n m factorial x pi, is equal to, goes to 1. And if m factorial x pi, x is not equal to n for any integer, n is not an integer, then cos square m factorial x pi whole to the power n will go to 0. We have already proved it. We already proved it, right? Here. So now therefore you have to check and observe the condition that, and you can understand if we put limit n tends to infinity over here again, if you now put, now iske upar if I put limit m tends to infinity, it will go to 1. Iske upar if we put limit n tends to infinity, iske upar again we will put m tends to infinity, the other iterated limit will go to 0. So therefore the question revolves around the fact that it exists for all x or not. Okay, so you have to understand that whether it exists for all x or not. Okay, so let's understand this very carefully. So what we are getting over here, we're getting that, yes, so this is the idea we're getting. So let's see now, when m factorial x is equal to an integer, when m factorial x is equal to an integer, so x must be equal to n by m factorial, right, for some n. Let's not call it m, it's a different n over here, let's call it k. Should be k, not that n is equal to k. Okay, so it should be this, And you can understand from here that any, so there exists any p by q, there exists a rational number for any p by q can be expressed as this, right? Q factorial times q minus 1 factorial times p. So this is equal to k and this is equal to m factorial. In fact, for all m greater than equal to q, it can be written like this if x is p by q. For all m greater than equal to q, x is this, m factorial x can be written as k. Okay, that is always true. For all m greater than equal to q, it can be written like this. That means what? That means since their limit m tends to infinity, so therefore it turns out that cos square m factorial x pi is equal to 1 for all m. So if x is equal to p by q is equal to 1 for all m greater than equal to q. We have proved it already, because we will take, because it's very simple, because x can be written as then p into q minus 1 factorial by q factorial, and every single time one number is added, we will add that number, so it will become q plus 1 factorial. So it can also be written like this, q plus 1 into q plus 1 by q plus 1 factorial. So it didn't like of this format, k by m factorial always. So that is the main aim. So therefore we can see that for all m greater than equal to q, it can be like this. So therefore limit m tends to infinity also, since m tends to infinity, after a certain point q, since it's m tends to infinity, this will go to 1. And if x is not an integer, x is not an therefore it will always happen for if x is equal to p by q, this limit will always be 1. If x is not a p by q, that is x is irrational, what will happen is the following, that this will be never 1. This will be never 1. And therefore it will be always less than 1. So we can use like this, we can use the inequality like this, that cos square m factorial x pi is always limit n tends to infinity. If you fix a m, if you fix a m, this will go to always 0. If you fix a m, understand this very carefully. If you fix a m, this will always go to 0. Why? Because cos square m factorial x pi is always less than 1. If you fix m, okay, and if you put m whole to the power n, this will go to 0. Understand this. This is where you fix m. This is where you fix m. If you don't fix m, then it can be different. But if you fix m, then this will be less than 1 always. In fact, it will have always a certain value, a certain fixed value, some alpha less than 1. Okay, this will be certain alpha less than 1 if you fix m, this alpha m. Okay, if you fix m. Now understand this. Now if you limit n tends to infinity, alpha m whole to the power n, this will go to 0, of course, because it's less than 1. So for the two different values of m, x, we get two different limits, 0 and 1, right? So this is the basic idea. This is the basic iterated idea. But here the iteration is very important. If m and n comes together, if m comes first and n comes later, then it can be a different case. So that's a homework for you. So if you fix x, then the limit is turning out to be something interesting. I hope you understood this. I hope you enjoy this, and all the best. And yep, so I'll think that if you're also, yeah, please do this homework, guys. If you fix m, you're getting this. If you don't fix m, if you limit m tends to infinity first and then n tends to infinity afterwards, you must find out what is the whole scenario. Okay, in that case, it will be oscillating in nature. It will be oscillating in nature. So what will you do in that case? Okay, that is super important. That is super important. So you think about it and you let us know in the comments box what you think about the opposite case, opposite iterated limit. Okay, so bye bye, all the best, guys, and I will see you in the next video. Stay tuned and stay blessed. And if you're looking for some crash courses to enhance your knowledge in mathematics, statistics, and probability for the IIT jam coming next year 2022, don't forget to check our link below. And if you're liking the video and this solver Volvo day, so do share your support by liking and sharing the video. All the best, guys, and see you in the next video. Stay tuned and stay blessed.